Good morning, good afternoon, good night. I'd like to present my work, which is combining single crystal fibers and ceramics to enhance ionic conductivity in solid-state electrolytes. First of all, I would like in advance to apologize for my broken English, and during this presentation I will go through the following topics: who I am and where am I, how to prepare single crystal fibers to serve as templates, composites with homo and heterointerface, some results of our ongoing research that we have so far, also some conclusions that we got, and some acknowledgements for all the financial agencies. Let's start with who I am and where am I. My name is Marcello Andreeta. I'm an associate professor at Materials Engineering Department at Federal University of São Carlos, Brazil. And my research topics of interest are photonic materials processing regarding to laser and microwave, clean energy, harvesting, generation, efficiency, single crystal growth with new and conventional ones, oxide glasses with laser processing, composites, and innovative devices. Where am I? So we should all be here at Lisbon. So if we go around the Atlantic, we can move to the rainforest, where everyone knows where it is, and we are far away from it in São Carlos University at São Paulo State in Brazil. So we can see the difference in distance from Rio de Janeiro. So this is all well-known cities from Brazil. This is our city, São Carlos, at state of São Paulo, Brazil. The title has an official title of Brazil's technology capital because of several universities we have in the same city. The average temperature during the year ranges from 9 to 29 degrees Celsius, and the population is around 250,000 people. This is our materials engineering department at our university. It was founded in 1972, which is very old for Latin American standards. It was the pioneer in material science and engineering in Latin America, and it has research groups on metals, polymers, and ceramic materials. So, why combining ceramics and single crystals? You might consider the case where it might be very difficult or even impossible to grow large single crystals. It might be too expensive to grow large single crystals for some application. And the composites might have similar properties with a lower cost. How to combine ceramics and single crystals? Basically, we can consider that there are two well-known different approaches for that. The first one, it's known as TGG, where it means templated grain growth, where you use a pre-reacted compound and adds all the conventional ceramic processing to it to generate the composites. And the other one is the RTGG, the reactive templated grain growth, where you use unreacted compound and added the same conventional ceramic processing to generate the composites. Which templates we can select to use to combine ceramics and single crystals? In our opinion, one very interesting case is to use single crystal fibers. But what are single crystal fibers? We can consider single crystal fibers as crystals where the crystal diameter divided by the crystal length is much less than 1. And there are some techniques to produce single crystal fibers. One of them is the laser heated pedestal growth. In the laser heated pedestal growth, a CO2 laser is used to heat a pedestal, we will show how we will produce it, and create a molting zone. And then the procedure is similar to a miniature floating zone. As we can see here, it's the same procedure as conventional, well-known floating zone technique. The pedestal preparation, in our case, were prepared just with a mixture of our oxides with the introduction of an organic ligand with this polyvinyl alcohol, and then we can, through a cold extrusion process, produce cylindrical pedestals. And this pedestal we use as it is without sintering the pedestal to produce the single crystal fibers. This is the case where we produce the lanthanum aluminate fibers and zircon fibers that we are going to use in this work. To avoid the diameter fluctuation, we developed in our lab the automatic diameter control based on an artificial vision system. It looks at the system looks at the molten zone and then control the laser power and the pulling speed to control the diameter. The reason that we think that laser pedestal growth is a very good technique to produce templates to combine crystals and ceramics can be seen in this slide, where we show several crystals that were produced by this technique, and we can see that we have a wide range of melting temperatures, and we can produce even crystals without congruent melting. In this way, you can search for the best lattice mismatch to combine your ceramics. In a previous work, we already done some work using strontium titanate templates in PM&PT ceramics. And we got excellent results regarding texturing the ceramics, as you can see here in the dielectric properties. So, what else is new, since we already did some single crystal fiber templates inside the ceramics? We think that we can improve the design of the electrolyte. If we think of an electrolyte as a material that can be between two electrodes, and we think we are searching for a better ionic conductivity in this solid state electrolyte, if we combine, this is our hypothesis, if we combine ceramics that can interconnect the two electrodes, it will create also, besides the single crystal fibers, it will create an interface that can interconnect the two electrodes without any grain boundary. That's our hypothesis, to try to improve or enhance the ionic conductivity on solid state electrolytes. Regarding the fiber ceramic combination, we can have homo interface, where the composition of the ceramic is the same of the fiber, and heterointerface, where the composition of the fiber might be completely different from the ceramics. Now I will present some of our results regarding the composites. We start with the homo interface, where we use yttrium stabilized zirconia fibers in a ceramic that is also yttrium stabilized zirconia. The composition was 8 mol% of yttrium, and the sintering temperature was 1600 degrees for 2 hours. We can see that from the EBSD analysis, in the ceramics you don't have any texture, so we have all crystal orientations from the yttrium stabilized zirconia. But here in the crystal, of course, we have just one orientation. What was interesting is that during the sintering process, an epitaxial growth occurs at the surface of the fiber, and we can see that we generate here also a single crystal that we call the interface between the two, so the ceramic and crystal. This interface, in the case of the ceramic, we call it crown, because it surrounded all the fiber. The Raman measurements in these composites have shown us that in this region of the interface, we observe a phase transition at the surface of the fiber from cubic to tetragonal zirconia. We believe that this occurs due to the high pressure that is involved in the sintering process. If we do a thermomechanical analysis simulation of the sintering process, we can see that the pressure can go as high as 2 gigapascal. In room temperature, we can correlate the Raman shift of the tetragonal phase with pressure, and we analyze it, and we can show that this region, the pressure can go as high as 1 gigapascal. In this way, this could be a method to produce self-strained interfaces here that could also be one of the reasons to improve or to enhance the ionic conductivity in zircon materials. Here we show a micrograph of this region, where we can see the phase transition from cubic to tetragonal in these composites. And when we measure the overall conductivity of the sample compared to the ceramics without fibers, we can see that we have an increase in conductivity regarding the effective grain conductivity when we analyze the fibers. The fibers within the ceramics give us an increase in conductivity compared to the ceramics itself. Regarding the heterointerface, we studied the lanthanum aluminate fibers in a matrix where you have lithium lanthanum titanate, LLTO for us here. And it is well known that it is very hard to produce single crystals of lithium lanthanum titanate. So in this way, we try to produce in situ crystals where interconnecting the two electrodes, as we said before. We can see here the ceramics with five lanthanum aluminate fibers, where we can see a very nice shaped crystals growing on the side of the fibers. We can see here again in a micrograph where you can see the crystals developed from the lanthanum aluminate fibers and the ceramic matrix. You have a very sharp interface here. When we cut the cross section, we can see the lanthanum aluminate interconnecting the electrodes and the LLTO, we call LCR, with this LLTO crystal region, interconnecting as well the two regions and without any grain boundaries here. And also the LLTO fibers with a lot of grain boundaries here, okay? In this way, we analyze also with rama to see if we are getting the same structure of the ceramics, and when we compare the LLTO ceramics with the LLTO LCR, this is the region, we can see we have the same structure. Of course, there are differences between the intensity of the bands because of the crystal orientation, but the structure is the same for unpolarized rama. We measure as well what could be the effect of the crystallographic duration of lanthanum aluminate fibers within the ceramics. So we use lanthanum aluminate fibers oriented in 110, 110 and 111 direction, and analyze the evolution with sintering temperature and time. So we can see that for 110 direction there are no evidence of increase the LCR region with sintering, yes, but with time it's almost nothing. It doesn't grow any crystals considerably along the side of the fiber. However, when we use the 110, we can see that increasing the time of sintering, there is also an increasing with the area of the LCR region. The same for 111. When we look to the optical photograph, we can see what we already said, that for higher temperatures, sintering temperatures, we get larger crystals, but with the orientation, we can see that with 100 we got almost very small crystals on the side of the fiber. And one very interesting feature is that when we get 110, we get a very anisotropic growth along the side of the fiber. When we look to those heterointerface regarding uniconductivity, we can see that compared to the ceramic without fibers, the crystals, the LCR regions, has much lower resistivity. And when we compare the overall enhancement of the conductivity compared to the ceramic without fibers, we can see that when, the same behavior of the LCR increases also the enhancement, and we got enhancement of the conductivity up to 200%. In conclusion, the laser heat pedestal growth, since it's a very fast crystal growth technique, it's a good one to prepare the crystal templates. The new template design, we have shown that it can improve the ionic conductivity in solid electrolytes. This enhancement in conductivity can go up to 200% in our case, and this might allow the development of new devices and or design. Finally, on behalf of the authors, we would like to thank Brazil and China's founding agencies, and also I would like to share our research motto from Tadahiro Sekimoto, that is, those who dominate materials dominate technology. Thank you very much for your attention.